Hello, I'm N J Wildberger. We're at the University of New South Wales. This is a problem on complex numbers where we talk about notions of modulus, principal argument, and polar form for complex numbers. So we're specifically asked to find the modulus, principal argument, and polar form of these particular complex numbers. This is problem 18 of our MATH1131 linear algebra notes. Okay, so it's a good idea to start by reviewing what these terms mean. Here is an Argand diagram where we visualize complex numbers. Here's a complex number a plus bi called z. And I remind you that what that means is that a is the x-coordinate of that point, and b, or bi, is the y-coordinate of that point. So we're thinking of the x-coordinate as being the real part. We'd say a is the real part of the complex number. And b is the imaginary part of z. That's terminology that goes back to René Descartes. Okay, so that's a very convenient way of thinking about complex numbers, but there's another way of thinking about complex numbers which is more in line with polar coordinates, where we're measuring where a point is by measuring, first of all, its angle and its modulus. Okay, so the angle is, by convention, the angle made between the positive x-axis and the ray joining the origin to the point z in question. And the modulus is really the length of this vector. So let's talk a little bit about those concepts, very important in complex analysis. So the modulus first of a complex number. So if we have a complex number z, then in fact the fundamental concept is really what I call the quadrants of z, which is the product of z and its complex conjugate. Okay, so that's a plus bi in this case times a minus bi, and that's a difference of squares which evaluates to a squared plus b squared. Okay, so I like to call this the quadrants of the complex number, and it's a useful notion. Then we obtain from that the modulus, denoted absolute values. So this is the modulus of z, or sometimes just the length of z when we're thinking about z as being a vector. And by definition, this is the square root of the quadrants. In other words, it's the square root of the product of z times z bar. And in terms of coordinates, it's the square root of a squared plus b squared. And admittedly, there's an approximate aspect because we generally can't evaluate square roots completely accurately. So we get a decimal approximation typically with our calculators when we use the square root. Okay, so that's the modulus. That represents the length, and it's often given the name r. Okay, so when we write down r in relation to the complex number, we're talking about its modulus or its length. And now we need to mention the argument. So the argument is an angle. So this is theta. Okay, this is the angle made between the vector OP, if this is the point P, Z as a vector, and the positive x-axis. And of course, because it's an angle, it is in principle multi-valued. So we generally like to measure angles in radians. So I remind you that with radians, if you go halfway around, then that's pi. And if you go all the way around, well, then that's 2 pi radians. And if you go some fraction of it, of course, you have some fraction of pi. Now, there's also the possibility of going around more than once, or the possibility of also going around in a negative direction. So sometimes it's useful to think about going around in this direction. Okay, that would be minus pi. So there's kind of a multi-valued aspect to angle, and there's then convention that we adopt in this course, which is not adopted necessarily in other courses. We say that the principal argument is between minus pi and pi. All right. That's a convention, just so that we agree that if we want to just have one particular value, we're going to stick with this principal argument, and it means that we're going to measure either in this direction like this, or we're going to measure in this direction like this. And if we're actually in that negative direction, we're going to say that that's pi, not minus pi. There's a bit of possible ambiguity there. All right. So these are conventions, modulus and argument, and now we can talk about the polar form of this complex number. Maybe we can write it here. So the polar form in its more familiar fashion is that we write z as r cosine theta plus I r sine theta. So we're replacing the a and the b. We're replacing a with r cosine theta, because this a is r cosine theta, and we're replacing the b with r sine theta, because this b is r times sine of theta. Okay? So when we replace the Cartesian coordinates a and b with these polar quantities r and theta, then we get the polar form of the complex number z. All right, so that's a quick review of these three important concepts. Now let's have a look at what these things look like for these particular complex numbers. All right, so here's a diagram of the complex plane, and the scale is a little bit bigger here to accommodate this first complex number 6 plus 6i. Let's call it z. Okay, so we want to find the modulus, the principal argument, and the polar form for this complex number. Right, so what we have to do is we have to find the modulus first. In other words, the length of this vector. So the modulus is mod z is the square root of z times z bar. Or in other words, the square root of the sum of the squares of the real and imaginary parts. 6 squared plus 6 squared. So the 6 squared can come out, and we're going to just have 6 times root 2. The angle, or the argument, is going to be, well, in this case, not too hard to see what it is. The angle is going to be pi on 4, because this is a 1, 1, root 2 triangle, and so that's a familiar 45 degrees, or pi on 4. So theta is equal to pi on 4, and that's in the range of being between minus pi and pi, so it's really also the principal argument. Okay. So there's the modulus, and there's the principal argument, and the polar form of the complex number would be z equals 6 root 2 times cosine pi by 4 plus I sine pi by 4. Again, bringing the common modulus out front and expressing the real and imaginary parts in terms of the cosine and sine of the argument. That's the polar form. Okay, let's have a look at the second one, which is the point minus 4. down here. So part B, z equals minus 4. Of course, that's an ordinary real number on our familiar number line, but we can still think of it as being inside the complex plane. And so it still has a modulus, it still has an argument. Okay, what is the modulus? Well, it's just the length from the origin, which is going to be 4. Or you could say the square root of z times z bar, so it would be the square root of 16, but you still get 4. What about the argument? Well, this angle here is going to be theta. That's going to be pi. And somebody might ask, well, isn't it also minus pi? And yes, the angle of pi and the angle of minus pi really represent the same direction. But we have agreed that for us, the principal argument always ranges between minus pi and pi with an equality on this side. So if there's any possible ambiguity, exactly in this case here, we're going to choose the angle to be pi and not minus pi. That's purely a convention that we're using here at UNSW and at other universities. There may be other conventions. In fact, often the angle is taken to be between 0 and 2 pi. That's also another very convenient and common convention. All right, so there's the modulus, there's the principal argument, and the polar form will be, well, z equals 4 times cosine of pi plus I sine of pi. And I hope you all remember that cosine of pi is minus 1 and sine of pi is 0. So this really does evaluate to minus 4 as it should. It's just another way of writing the complex number, not in terms of Cartesian coordinates, but in terms of this modulus and argument. Okay, let's have a look at root 3 minus I, which I suppose we can also put on our diagram here. So square root of 3 minus I, so it'll be down here. This will be root 3 minus I. And I have to remind you a little bit about just some basic geometry here. So z equals root 3 minus I. So I'll just remind you of this basic triangle here that comes up in this kind of situation quite a lot. The 1, 2, root 3 triangle. Okay? So if you have a right triangle with sides 1, 2, and root 3, this is a very familiar triangle because it's basically half of an equilateral triangle. And then this angle here is 60 degrees or pi on 3. And this angle here is 30 degrees or pi on 6. Okay, so of course very familiar because this is a common example whenever we're working with trigonometric functions in the usual way, because it's one of the few triangles that we can work things out explicitly. That's why we're using an example like this. It's basically a triangle based on something like this. So here it is right here. Maybe I'll draw it. Okay, and you can see that there is a root 3 in this direction and a 1 in this direction. There's a right triangle there. And so this side here is going to be 2. So the modulus z is going to be 2. And if we didn't know that from the trigonometry, we could also compute that by just using the formula that mod z is the square root of z times z bar. And so we would have to find the square root of, well, the coefficients are root 3, so we have to square that, and minus 1. So it's altogether square root of 3 plus 1, which is 4. And that also gives us 2. In terms of the argument, well, we need to know basically the angles in this triangle. So there's 1, 2, root 3 there. And I guess you need to know that this angle is the one opposite the 1 here. So this angle here, which is the one that we're interested in, might be a little bit small there. That angle is going to be essentially 30 degrees. But it's 30 degrees in a negative direction because we're not going in the positive direction, we're going in the negative direction. So the angle is minus pi on 6. Minus pi on 6, that is the principal argument. And it's within the required range between minus pi and pi. And so the polar form will be z equals, the modulus is 2. And then we have cosine pi by 6 plus I sine pi by 6. And maybe it might be useful for me to mention the alternate form for the polar form, the exponential form, where you write cosine pi by 6 plus I sine pi by 6 as e to the I pi by 6. It's another way of writing that expression. So that's those are the first 3 examples. Okay, now let's have a look at these last 2 problems. So the first one is z equals the point minus 1 over root 2 minus I over root 2. Now, it might not be immediately obvious, but this is a somewhat special complex number because it turns out that it lies on the unit circle. Those complex numbers whose modulus is exactly 1. Here, my rough picture of the unit circle. Of course, with equation x squared plus y squared equals 1. But in terms of complex numbers, these are the complex numbers whose modulus is exactly equal to 1. And how can we see that for this one? Well, the modulus of z is square root of real part squared plus imaginary part squared. And that's, of course, square root of 1/2 plus 1/2 for a total of 1. So that complex number really does lie on the unit circle. And because the real and imaginary parts are equal, it's kind of obvious that this is at a 45 degree in this direction. So that this angle here, theta, is in terms of radians now. Okay, so we're going 9 degrees plus another 45. So it's 3 pi by 4 in the negative direction. Okay. So it's minus 3 pi on 4. That's the argument. And so the polar form for z is z equals 1, okay, times cosine minus 3 pi by 4 plus I sine 3 pi on 4. And the 1 here is not really necessary. But if we're going to put it there, we should put another bracket here to close it off. Okay, now let's have a look at a sort of more random complex number, one whose coefficients are not chosen carefully so that we end up on a 1, 1 root 2 triangle or a 1, 2 root 3 triangle. Okay, but then we have to expect that we're not going to be able to write down the cosines and sines and the relationships as simply as we can for these more special cases. We may have to go to the calculator to make some calculations to find angles and moduli. Okay, so here it is here. Minus 7 plus 3i. So we're going minus 7 in the x direction, 3i in the y direction. So here's the complex number somewhere over here. We can see that the angle is in this second quadrant. And, okay, how are we going to find the modulus and the angle? So this is question E, maybe in blue. All right, so z is equal to minus 7 plus 3i. Well, the modulus is as before. It's the square root of the real part squared plus the imaginary part squared for a total of square root of 49 plus 9, which I guess is 58. So square root of 58. And again, in practice, you'd have to get your calculator to spit out some decimals for that, and you'd really only get an approximate answer. Okay, what about the angle? Well, that's a little bit trickier. So how do we find the angle in general when we have a vector like this? Well, we know that the tan of the angle is y over x, the ratio between the y coordinate and the x coordinate. So in this case, y is 3 and x is minus 7. So we're getting that tan theta is minus 3/7. All right, so we need to invert that, use a inverse trigonometric function. But we have to be a little bit careful because of the particular position of this. So we'd like to say that theta equals arctan of minus 3/7, or alternatively tan inverse of minus 3/7. But that's only if you interpret these inverse functions in a rather general way. If you actually use your calculator, you're going to have to take into consideration the fact that this other direction over here, this angle here, which differs from this one by pi, will have the same tangent. And so when you're calculating arctangent, your calculator is going to spit out that angle and not this angle. So to compensate for that, we really need to add pi to these values that your calculator is going to give you in order to get a theta value which is in the right range. Okay, so what is this? I made a It is 2.736 700, and then it carries on in some fashion or another. Okay, so we can only get that angle approximately, just part of the fact of life, that what happens when you work with angles and not with rational trigonometry. But in any case, this is an approximate solution, and so we get the polar form would then be, doesn't look that pretty, but it would be z equals square root of 58 times cosine of 2.736 dot 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 plus I times sine of 2.736 dot dot dot. And really, we're really just getting an approximate expression for the complex number this way because of the inevitable approximations involved in these inverse trig functions. All right, so there's a range of examples of calculating the modulus, the principal argument, and the polar form for some complex numbers.